Hey everybody, hope you are doing well and you had a nice weekend. So in order for us to avoid missing a class, and I really want to keep on top of things and get you guys to learn some of the new concepts, we are going to continue in this discussion learning about acids and bases and how this relates to equilibrium. So just a quick recap about equilibrium. So at this point, we've talked about the fact that most of the reactions that exist do occur in both directions. They are reversible. And what that actually means, again, is that when equilibrium is achieved in a chemical reaction, the rate of the forward and reverse reaction is the same. So this was something we talked about before, so that was just a quick recap. Now what I want to do is I want to get into how that relates to acid and bases. So your teacher who is covering right now should have given you this PowerPoint. So what I would like you to do is kind of pretend like we're in a regular class and you're going to write down the notes and what I write on the PowerPoint. And then we can go through it tomorrow and just make sure you guys are comfortable with it and move on. So we're not actually going to cover everything today, but we're going to cover majority of it. Okay. Shh, Sammy, stop. So, sorry, just ignore my dog. All right, so just in general, what we've learned about acids and bases. So this is something that we talked about in the past when I taught you guys this in grade 9. So acids are characterized by the fact that they have pH is going to be less than 7. They turn litmus paper red. This is something we will be doing in our lab. They taste sour. That we will not be doing in the lab. They're corrosive, and some examples would include like fruit juices and sodas and coffee. Bases, on the other hand, are the opposite. So their pH is greater than 7. They're going to turn litmus paper blue. They typically taste bitter. So if you've ever accidentally eaten soap, it's a very bitter tasting thing. They tend to feel slippery, and some examples include baking soda, ammonia, and soap. So here is the pH scale. It goes from 0 to 14. And if you recall, the further you get away from 7, which is neutral, the strength of the acid or base is going to increase. And also recall, and we've talked about this lots of times, that a neutralization reaction is characterized by when you have a strong acid and a strong base mixing and you end up creating salt and water. And since water is considered a neutral substance, that's why it's called neutralization. Okay, moving on. So there are a number of theories that relate to acids and bases. So I'm just going to kind of briefly go through them. And I think this picture is pretty self-explanatory. So theories. So the first one, which is the blue one here, this is the first theory. So this scientist was a Swedish scientist that was the first to come up with the concept of acids and bases in 1887. So what basically his theory comprises is basically what you've learned from me up to this point, is that if you have this, the hydronium ion, or it's also called the hydrogen ion, right? That would be considered an acid. And then if you were to have the hydroxide ion, that would be then considered a base, which isn't inaccurate. It just unfortunately doesn't explain every situation and characteristics of different reactions with acids and bases. So it's not actually completely accurate in every situation. So the next theory that we're going to be focusing on mainly is the Bronsted-Lowry theory. And what this one involves is a donation of a proton So remember, and I think we talked about this quite a bit last year, was that the hydrogen ion, the H plus, is actually just a proton floating around. So if you have one proton and it's being passed between different substances, if the substance is donating a proton, then actually it's going to be classified as an acid. And if a substance accepts a proton, it's going to be classified as a base. Now, the other theory, which we're not going to be talking about today, is the Lewis theory of acids and bases. And this theory basically is using the concept of explaining how acids and bases behave based on the exchange of electrons. Okay, so that's just kind of the gist of that. Let's move on. All right. So according to, like I just mentioned, but I'm going to write it down this time, and this picture kind of shows you what's happening. Here is our acid, and here is our base. How do we know this? Because this hydrogen here is going to be leaving this substance and going to this one, as you can see here on the opposite side. So the reason that A is classified as an acid is because it lost that hydrogen, lost that proton. It went to the other molecule here. So that is therefore its classification. So an acid is going to donate protons. And in this case, the proton is in the form of the hydrogen ion. And in the case of a base, as you can see here, the base is taking or accepting the hydrogen ion. So that is actually the definition of an acid and a base if we're using the Bronsted-Lowry citric acid-base reaction. This one is better than the previous one of just being hydrogen ions and hydroxide because it explains the behavior of acids and bases. And if you notice here as well, most of them, not all though, we'll talk about that briefly, are going to be in equilibrium, which means the forward and reverse reactions will occur. So as we can see here on this side, the A, I'll talk about what this means in a moment. The A is now going to receive the hydrogen back when it goes to the reverse reaction, and the B will give away that hydrogen back to the A in the reverse reaction as well. Okay, I'm going to give you some examples of this because one of the things you're going to have to be able to do is identify what are the acids and what are the bases in different types of reactions. So I'm going to show you this one. So the first one would be water in liquid form plus hydrogen chloride in solid form. So what's going to happen in this scenario, all right, is when they react, this is what you are going to form. Okay, so if we look at this, all right, which one then would be considered the acid and which one would be considered the base? So I can pause for a moment and you can look at it, and I would ask you normally what the answer would be, but since I'm not with you, I'm just going to tell you. If you notice here, this hydrogen went to the water. So that became the H3O, which we call the hydronium ion, which is a classification, if you recall, of acids and bases. So since that hydrogen went to the water, then this would then be considered the acid, and not because it's actually called, like hydrogen chloride does become hydrochloric acid in solution. This is the acid because it gave away the hydrogen. And then water in this case here would be a base because it accepted the hydrogen. Now let's take a look at another situation where we have ammonia in solid form. And we're going to mix it with water in liquid form. Now, can you predict what you think is going to happen here based on your knowledge of previously of acids and bases? So in this case here, the water is actually going to be donating a hydrogen, okay, to the ammonia, the ammonia creating ammonium and the hydroxide ion. So in this case here, because this one accepted the hydrogen from the water, then in this case here, this would be the base. And the water in this case would actually be an acid. And again, it's based on the fact it's all about where does the hydrogen go. Notice that, and this is a key thing, that water can be, depending on the scenario, an acid or a base. And that brings us to our next slide. So the term for a substance that, depending on the situation it's in, whether it's an acid or a base, is called amphoteric. Okay, so it can be both, but depends on the situation. So let me give you another example. And this was actually, if you did the gizmo that I asked you guys to do last week on the ocean base equilibrium, this will look familiar to you. Okay, so here we have the bicarbonate ion, and we're going to react it with water. Now, in this case here, this is a reversible reaction. Okay, in some situations, we will see this happen. No. So in this case here, what happened? So what would you classify the bicarbonate ion as in this scenario? Is it going to be an acid or a base? Well, in this case here, because it accepted the hydrogen, it would be a base and the water would be the acid. So that does happen. But in other situations, you could have this happen. So you should remember this. This was in that gizmo. All right, so if you take a look this time, what happened? Well, this time, the hydrogen was donated to the water, creating a H3O ion, and then you have a CO3 ion, the carbonate ion. So therefore, in this case, since it donated it, that would be the acid, and that would be the base. So this would be an example similar to water, and it's dependent on the situation, where you could have it being one or the other. Okay. Let's talk about reversible acid and base reactions and then relate it to strength of acids. So I'm going to give you an example of how you kind of analyze these different things. We're going to be bringing up now the conjugate pair of acids and bases. So if we take a look, this is acetic acid. And we are going to react it with water. Okay, now acetic acid is actually a pretty weak acid. It's the one that's found in vinegar. So what happens if we're looking from a forward reaction? This is what we see occurring. And we create the hydronium ion. Okay, now if we look at it for going from a forward reaction, this is your acid, this is your base. Now, this is, though, a reversible reaction. So if you are going then the opposite way, what's going to happen is that hydrogen ion that is found on the HVO right now is going to go back to the acetic acid molecule, and it's going to form the acetic acid again. So in this case here, this side, this would be what we call the conjugate base, because when we go back in the reverse direction, it's accepting the hydrogen. And then since this is giving away the hydrogen, this is going to be the conjugate acid. So conjugate is the word that is used when you're talking about a reverse reaction. And then what we can say, what chemists also say, is you have conjugate acid-base pairs. So for example, this would pair with this. So this is an acid and then it's conjugate base. That is the phrasing that you would use for it. And then if we look at the H3O here, that's the base and that would be its conjugate acid pair. Okay, so this is something you're going to have to be able to do, is look at a reaction and decide what's the acid, what's the base, what is the conjugate and acid and base, and what are the base pairs. Okay, let's get into strength of acids and bases. So it's not what you think. I always thought it had something to do with, the pH, and if you have like something that has a pH of 1 versus a pH of 4, yes, that is kind of a measure of strength, but it actually has to do, if we're looking down at what exactly is happening, it has to do with the attraction to the proton. So I just write down strength of acids and bases, and I'll show you what I mean in a moment once I write it down. So here's just some examples of weak and strong acids and weak and strong bases. So we're looking at now what that actually means. So if something were to be classified as a strong acid, I'll put it here. For something to be considered a strong acid, it's going to have a weak attraction to the hydrogen ion or the proton. Because if you're going to have an acid giving away, because that's what our definition of an acid is with the Bronsted-Lowry, then a strong acid is going to easily, readily give away that hydrogen ion. Now, a base, on the other hand, if we're looking at a strong base, it's going to be the opposite. So a strong base is going to have then a strong attraction. Sorry, for some reason I can't write on the spot of my screen, so I'm going to write down here. Strong attraction to the hydrogen ion. So it's readily going to accept that hydrogen ion, like very, very easily. It's going to have a strong pull on it, and then it's going to form a strong base. So that's kind of what that means. Now, how do you even know this though? So we're going to just go back for a moment, and I'm going to show you some of the different chemical reactions that we talked about. Okay, this one here, this first one. So hydrogen chloride, when it is, or even hydrochloric acid, it's classified as actually as a very strong acid. So that would mean that it readily gives away its hydrogen ions. Whereas ammonium hydroxide is considered a strong base because it easily takes away those hydrogens. Now there is a way to measure this, and it's called the percent ionization. And you can calculate this, and what happens, and I'm not going to actually have you calculate it, I just want you to understand it so that if it comes up eventually, you'll know what I mean, okay? So if I were to talk about, for example, a strong acid, right? And we know that a strong acid donates those hydrogen ions. Now, let me show you what I mean by that. So if you were to react the hydrogen chloride with water, and you were to look at the initial concentration of the acid versus how much was ionized, what percentage was ionized, what you end up getting in this scenario is 99% was ionized. Now, what that means is like this reaction, although it is in equilibrium, basically the forward reaction is always favored because of the fact that that reaction, has such a weak hold that 99% of that, if you find it in solution, is going to be this being pulled away and going to the water. So that would be an example of a very strong acid. So it's weird. It's kind of the opposite to what you would think. So a strong acid has a weak hold. Okay, this has a weak hold. Okay, on that. Now, what if we were to compare it to a weak acid? So I already mentioned to you guys that acetic acid is considered a weak acid. So if we were to talk about something being in a weak acid, what would we say? So in this case, the hydrogen here actually is held pretty tightly to this ion. So when it's undergoing a chemical reaction and forming, there's a strong hold on this hydrogen. So it's not going to completely ionize like our first one. In fact, it's been calculated to be, using this formula here, only 1.3% is ionized, which means, again, there is equilibrium. However, most of it is going from the reverse reaction. You're not actually getting a lot of donation of that proton. So that would be considered then a weak acid. Okay, how much time? Okay, I'm going to stop there for today. And what we'll do tomorrow is we're going to talk about this weird thing called autoionization of water. And I'm going to teach you guys, and I did actually teach this to you years ago, but we're going to go through it again, is how to actually calculate the concentrations of hydroxide and hydrogen ions in concentration. Okay, so there's going to be a little bit of math that comes into it. So we will stop there. Hope that wasn't too boring, and I hope you have a great day. Take care. Bye.